We got this.
Oh, Jonathan.
Yeah. Hey, can you hear me all right? Woo! Cool. So my name's Jonathan. I'm a PhD student in the physics department at Purdue. And when I want to sound cool, I tell people I study cosmology. So, let's keep like that.
You want to just stand up?
Okay, cool. Yeah. Okay, so I've been told that when you've had a couple drinks, that's when you're really ready to ponder the big questions. So, here's a couple big questions motivating my research. How does the universe behave? What causes this behavior? And the one that's probably the most philosophical, what really is empty space? So that's the one you probably need to make sure you finish your first drink before we get to. Okay, so all you'll do, in the beginning there was a universe. So here's a model of the universe, but what is it going to do? Is it just going to stay here and not change? We call that static situation. Or does the universe get bigger? Or does it get smaller with time? So 3 possible behaviors. Some of you might already know the answer, but how many of you think the universe should be static? Getting bigger? Getting smaller? Well, seems most of you already know the answer, but this question was mainly just metaphysical until about the 1920s, when the most famous physicist of them all, Einstein, was doing some math. So, Einstein's a pretty small person. You probably know that he came up with the theory of relativity. Yeah, so this equation right here, you don't really need to worry about what it all means, but this is what we refer to as Einstein's field equation, and the term with the big G stands for gravity, and the R's stand for how space behaves. Okay, so Einstein figured out this equation for relativity, and he noticed something. This equation predicts that the universe will be getting smaller with time. That gravity will cause the universe that is just sitting there to collapse. Now, Einstein and most of the physics community at the time were like, the universe can't do that. It has to stay the same. It cannot get smaller. They also didn't think it was getting bigger. It was just going to be static. So, what Einstein did to solve this problem, he just introduced a new constant, just slapped it into his equation, and said there must be some energy in space that's called the cosmological constant that cancels out gravity. So if gravity wants to make the universe get smaller, the cosmological constant pushes back out. And we get a universe that does not change with time. Okay, so this was where cosmology stood at about 1915. We decided there must be some energy in space. I'll get to what that energy is in a moment. And this energy is such that it cancels gravity. The universe does not change. Okay, however, Einstein was a theorist. And I'm also a theorist, so I'm not making fun of him, but that means he's thinking about things and trying to make sense of stuff. He's not the one who's actually collecting the data. If you collect, however, what makes physics and science different from philosophy, you need to agree with observations. So there's a bunch of observational astronomers, such as Edwin Hubble, that guy there in the behind a massive telescope. He's the guy the Hubble telescope's named after, who are looking out in space and taking measurements. So, one thing you could do is look at stars and galaxies. Hubble was the one who actually proved there were other galaxies besides our own. Fun fact. So, stars, as you probably guessed, send out light, and we can absorb that light. However, what if the star is moving? Everything's moving in space. The planets are revolving around each other. Our sun is moving. So it's very unlikely that everything will be stationary. So what does movement like this, very exaggerated, do to the light that comes in? So if stars are sending out light, you can imagine that it's like a tennis ball hopper machine just throwing tennis balls out at you. So if I'm just throwing these balls out at you, you'll be catching them, hopefully. And when you catch them, if I'm just doing it constantly like this, there'll be so many balls that come to you every second. We call that the frequency, how often this happens. Now, if I was to start to move, let's say I'm moving backwards, the balls now have to travel a farther distance. So what does that mean about the time it takes for the balls to get to you each time? It's going to be longer. So we say it's now a less frequent event. Conversely, if I'm running towards you and throwing, what happens to the time?
It's more frequent.
It's more frequent. So, this happens to light, but instead of tennis balls, we deal with waves. So, if light is getting less frequent, all of these bumps here kind of indicate how many events happen. So you could say light is made out of photons, you get all of this wacky quantum mechanics, but let's not worry about the quantum right now. Let's just say we can model the frequency that the light is being sent out by the star with this wave. So if star's moving backwards, we say it's getting less frequent. That means our wave gets stretched out, and this is referred to as redshifting. You're getting moved to a red part of the electromagnetic spectrum. Now, conversely, if you're getting closer, it's going to be more frequent. You get pushed to the skinnier side of the spectrum, which is blue or violet, but this is called blue shifting. Okay, so if a star is moving, we can see what color the light appears to be and walk backwards to see if that light was stretched or compressed. So, and this is a more simple picture showing that. Okay, so Hubble was looking out at space, and all he did was take a bunch of measurements, and he realized that things are moving apart. So what I mean by that, if these purple dots were our stars, there's two ways things could be moving apart. He noticed all of these stars had redshifting. So everything was moving apart. Oop.
Just keep it.
Yeah, so Hubble realized everything's moving apart. Now, there's two ways things can move apart. You could either be moving apart just because you're drifting away from each other, or you could be attached to something which itself is stretching. So if I was to imagine a rubber band, okay, and if you take a rubber band and you put a lot of dots on the rubber band, and you stretch the rubber band, the dots that are farthest away from the middle will actually stretch a lot more than the dots closest to the middle. So that indicates that the dots are moving with something that itself is stretching. We say the amount of displacement is dependent on distance, so there's something expanding. The other way you can move apart is if you're just walking away from each other. If that is how things are moving, the distance away you are does not affect how much you got away from something else, because you're just moving regardless of everyone else's position. So that was kind of what I was trying to get to with the dots that disappeared. But what Hubble noticed was that these moving stars were moving such that the farther away they were, the more they moved away, which meant that the stars were attached to something that's getting farther and farther apart. Well, the only thing the stars can be attached to is the universe itself. So, okay.
I think it's just a little hot in here.
Okay. Yes. So, well, I can share the joke I heard at a teaching training I was at Saturday. Why did the chicken cross the playground? To get to the other slide. Okay, so drifting apart just indicates that you move away from each other. However far you are doesn't affect how much you spread out. Something expanding, the farther dots, this one is so far it's not even on the screen anymore, get stretched even more as the material stretches. Now, if there's any math majors in here, they might tell you that my ratios are slightly off, but I just care about the general idea. Okay, so, in essence, Hubble was like, hey Einstein, everything is shifting away from each other. So the universe is actually getting bigger, and a popular demonstration of this is if you were to take a balloon and stick a bunch of stars on here, and you blow up the balloon, you, for yourself, could see that the stars that are really close to each other spread out some amount, so the red and yellow are rather noticeable, but this red and blue one gets stretched really far apart, and if you take these measurements, you can see that the farther something is apart, the more it stretches. It's not just shifting the same amount. Okay, so we discovered the universe is getting bigger. Well, now the follow-up question is, how is it getting bigger? Like, if you look at my niece, she's getting bigger with time. However, she eventually will stop getting bigger in about 10 years or so. So is the universe getting bigger and slowing down as it's getting bigger? Is it just getting bigger and bigger constantly? Or is it getting bigger and bigger and bigger, and the rate is getting bigger, it's getting faster and faster and faster? Well, so Hubble was the 1920s. It took 70 more years for this to have any progress. So, we measured a bunch of things called supernova, which are just really bright explosions of stars. And the nice thing about supernova are we know exactly how bright they should be and what color they should be, because the conditions you have here is called a type 1a supernova, are so precise that regardless of where you are in the universe, it's going to be roughly the same color and intensity. However, remember, we're observing the universe, so we need to account for how much the color gets shifted and how much dimmer it gets. So this gives us two important pieces of information: how far away the supernova is and how fast it's expanding away from us. So if you wanted to do some Googling, this was 1998, the keyword type 1a supernova surveys. There were actually two of them going on at the same time. So, what the surveys found is that the universe is getting bigger, as we already know. But there's something I also neglected to say. The farther away something is in space, the more time it takes the light to get to us. So that means when we're looking back in time, well, when we're looking at space objects far away, we're effectively looking back in time. So the shifting we see is from farther away in time to farther away we're looking. It's a bit to keep track of, but if you do a lot of math, and they probably use computers at this point, you can see that the rate of expansion in the older universe was smaller than the rate of expansion now. So the universe is getting bigger at ever-increasing rates. And that just really was confusing to people, because why is that even happening? It's one thing for the universe to get bigger, but it's constantly getting faster as it gets bigger, and that just, again, didn't make sense. What this meant was there had to be some energy to constantly be driving this to get this ever-increasing expansion. So, you need to do some thinking now, and the question was, where was this energy coming from? And what is the way to make the universe's rate of expansion get bigger and bigger? So a key thing about the expansion was, it's expanding everywhere at the same rate. Yes, if you go back in time, there's a difference, but at the same time, the expansion's uniform. So that means there's something spread out throughout space uniformly, such that everywhere in space has the same expansion. Which also means there's not a center of the universe, because everywhere looks the same. Which also means you can pick any center you want. So, okay.
No center?
It's no center. There's an observational center because we can't see farther in one direction than the other, but... Okay, so there has to be some energy driving out space, and physicists, astronomers, refer to this as the dark energy because we can't see it. So where does it come from? So one possibility is that space itself provides the energy. Because space is everywhere, so naturally, the only thing we know that is the same everywhere is space. So maybe there's energy in space itself that does this. Now this is the part where you might want to start drinking a bit more, because we're going to be talking about empty space. But before we do that, we're going to go a step back a bit to talk about classical mechanics. And something you may have learned about is called force. So if you want to make something move, it requires a force. So if we have the soccer ball here, the guy kicks it and changes how the ball moves, right? His foot is applying the force. However, the ball is coming back down. That's not his foot. What's making the ball fall back down?
Gravity.
Gravity, but I don't see a hand from the earth just grabbing the ball and pushing it down. So there's something that's causing this ball to fall back down. So it's gravity, but gravity does not act like a foot. It's not touching anything. We say there's something we refer to as a field. So a field is something invisible in space that you can't see that causes objects to move with the field. So for gravity, this might be moving, yeah. For gravity, my apple's not actually falling, is it? Apple. So for gravity, that will cause this apple to gradually want to fall, despite the fact there's nothing touching it. Now, could say that's just how gravity works, but there's actually other invisible fields out there. You've all had refrigerators, I'm assuming, and you all use magnets. If you play with a magnet, you can feel that there seems to be something in space that makes it hard to push two Thomas trains together one way, but the other way they just want to move. So there's a field in space, so that's just what I mean by field. Something invisible causing things to move. Don't really need to understand it, but just accept for now that these exist. So, now I get the more complicated words. So, it turns out that in addition to gravity and magnetism, there's a bunch of other fields out in space. We refer to this as, this study of physics is quantum field theory, which is like the two most scary words in physics thrown together. So classically, if you want to go with me, if you have a ball, the ball just exists in space. Quantum mechanics says, no, you don't have balls, you have these objects like electrons that follow probability waves. What does that mean? We can talk one-on-one, but just need to get through this. Quantum field theory says, no, the quantum mechanics is wrong, that fields, those invisible things like gravity and magnetism, exist through all of space. And particles are excited fields. So what do I mean by excited fields? So if I had a wave, and maybe you can see this, what this machine is doing is just vibrating a warp really fast, and you can see this wave. The number on the side is the frequencies, how fast you're jiggling it. So the faster you jiggle this wave, it gets more frequent. You see more parts of the wave. It goes from one part to those two pieces, etc., etc. So that's how waves behave, and excitation means the wave has more energy, there's more frequency. So, in quantum field theory, I'm going to use my hands now. You have a wave that's wiggling in space. If you make the wave more energetic, it doesn't get shorter like those warp waves. Instead, when you add more energy, it doesn't know what to do with the energy, so a particle pops out of the field. So the wave keeps wiggling the same way, but now you have this droplet of energy that we refer to as a particle. Now, that is kind of cool if it actually is how things work. And I'm going to tell you it is, but you can go look things up yourself and challenge me. So, we have these particles come from quantum field theory. They're excitations of energy. Well, if the particles are coming out of the field, we can't see the field, but the field's wiggling, which means the field by itself should have some energy, even if it's not enough energy to pop and create a particle. So, the question is, do these fields actually exist? So, I had a picture, but if you were to look something up called the Casimir effect, what this means is, so I'm saying these fields, they're wiggling throughout space, and each field corresponds to a different particle. So you have an electron field, you have a Higgs boson field. I'm simplifying this a bit, but that's the general gist of it. So if these fields exist in space and they provide energy, what we can do is imagine you take one sheet of paper and then you take another sheet. So if you do this with regular paper, we're not small enough. You need to get really, really small. I guess the Marvel films will call it the quantum realm, but there's a lot of issues with that. But if you get these pieces of paper really close to each other, and instead of calling them paper, you'll call them, there'll be some type of metal sheet. And you get them so close together, we're going to say they're closer together than the regular thickness of a normal piece of paper. Okay, so there's still some separation between them. So that means there's some space in the middle, and there's a lot of space on the outside. Well, what happens in that situation is, if quantum fields exist, that means you should have a lot of wiggling space on the outside, and my picture should show up soon, and a tiny amount of wiggling space on the inside. Cool. Nice, nice, nice. Almost there. So, there's my particles or excitation. So we have fields existing in space, and we take some plates. So what this means is these big waves, they can fit on the outside. But the fields that have smaller waves fit on the inside and the outside. So on the inside, you have a tiny amount of field, which provides energy, and energy wants to push things apart. However, on the outside, in addition to the tiny waves, you have these huge fields as well. You have many, many, many more fields that also want a push. So there's going to be more push to get these guys together than to push them apart, which means they should collapse. And physicists did this, and they found that these plates collapsed together. So there was nothing else going there. We measured it. We did some clever math and physics to make sure it was not gravity. It moved differently than if it was just gravity, and differently than if it was just magnetism or the electric force. So that kind of indicated that these fields exist in space. Okay, so we're almost to the end of our journey. So, in physics, there's something called the Standard Model. I only added it here because some grad student might yell at me if I didn't, which is every particle we know about. Okay, so each of these particles will have different fields. So, if we calculate the energy of their field, we can add all of these energies together. Now, some of the fields actually have negative energy. That means they want to pull things together. Some of them have positive. They want to push things apart. Okay? So, you add all of these fields together and we can calculate that the energy in space is in units that sound really weird. 10 to the 112 joules per centimeter. That should be cube, is the density. My bad. Okay, joules are just unit of energy. You probably are familiar with joules. What this is saying is if you take a centimeter cube, just this cube of space, there should be that much energy in it. However, that does sound like a huge number, doesn't it? Well, if you do the observational data, what the supernova observations tell us is the energy should actually be 10 to the minus h, which is a lot smaller. And this is where you just kind of get frustrated because the observation, well, the prediction is 1 with 120 zeros times larger. So if there was a credit mistake like that, you would never be paying your debts. So that's a huge number, and this is where physics is at this moment in time. We know there's energy density, but we don't know exactly how to calculate it, and when we try, we overestimate by a ton. So, this problem is given a name called the cosmological constant problem. However, in my thesis, I called it the cosmological calculation conundrum. I think that's more catchy. So, for the past 20 plus years, physicists have been trying to solve this problem. Now, my research is trying to solve this, and what we consider is, well, obviously, what we've done doesn't work. So, maybe two possibilities. There's more particles out there we haven't discovered yet, or can the fields combine together and composite into new fields that behave differently? We don't know. That's what my research is trying to figure out, is why is there a problem? Is it actually something we can solve using quantum field theory predictions? It's a lot of coding. Maybe it's something entirely else, and maybe it will take until the next Einstein comes along to introduce a whole new idea. But this is the state of physics today. So I don't have an answer for you of why the universe is getting bigger. If you want to learn more about any of this, I highly recommend anything by Brian Greene, particularly The Fabric of the Cosmos. If you want to hear more about Einstein's side of the story, probably the best Einstein biography is by Walter Isaacson. I only recommend books I've actually read, so. And if you want to hear more about this stuff but don't want to read non-fiction, I also really like the Free Body trilogy by Cixin Lee, which talks about a lot of this cosmology stuff in very absurd science fiction fashion, which is quite entertaining and also quite existential when you get to the last book. But it's called Death's End, so what would you expect? If you enjoy listening to me talk, I make science videos on my YouTube channel, Heroic Science. And one last thing, I'd like to thank Astronomy and Tavern for organizing this. the Spot Tavern for hosting this. Make sure you support them, small business. My collaborator, the guy I'm standing next to, Dr. Craig Pryor, at the University of Iowa, not Purdue. So if you want to harass him, you need to go to another state. And all of my friends in physics, thank you.
All right, not to jump anywhere yet. If anybody has any questions, feel free to have time for like 1 or 2, and then we'll take a break for people to get another drink and for me to set up any projectors.
Sorry, I forgot those questions. It's not a lecture. So, questions? Yeah?
I have a facetious question.
Okay.
Have you tried asking ChatGPT?
You know, I have it myself, and it's a bit funny. My advisor, Craig Pryor, I were talking about ChatGPT last week, and he was trying to get it to talk about some other physics problem and asked it what references should I use. And it made up a paper written by him he never wrote or published. So, I'm not sure how trustworthy it is.
Interesting.
Yes. Any other questions? Yeah?
How does space-time play into the field
Field
issue?
thing? Yeah, so I kind of know of the general relativity stuff. Basically, everything I talked about was referring, my slides don't matter at this point, is referring to stuff that is static, as in relativity really plays into things when something's changing its velocity. So, if something changes its velocity, what happens is, as you move through space, you're moving through space and you're moving through time. So if something's moving faster and faster, it actually has time tick even slower for it, which makes math a lot more complicated. So what the space-time thing is telling us is that the reason we can talk about the universe as something kind of controllable is that there's a limit to how fast everything can go. That's called the speed of light. It adds some finite things to all of our calculations. Otherwise, if you didn't have relativity where your space and time speed could change, things could go to infinity, like much bigger than 10 to the 112 bigger. So the space-time stuff, I'm not really going to get into it, but it kind of allows us to have this more controlled universe in our calculations. However, that really plays in when things are moving. My research is looking at empty space itself. So if space is empty, there's nothing moving in it for us